Hello everyone, it's April the 17th. Let's do this island parameter. You are given row by column grid. 1 represents land, 0 represents water. Grid cells are connected horizontally, vertically. The grid is completely surrounded by water, and there is exactly one island. The island does not have lakes, meaning the water inside isn't connected to the water around the island. Wait, hold on. It doesn't have lakes, meaning the water inside isn't connected. Yeah, one cell is a square with side length 1. The grid is rectangular. Width and height don't exceed 100. Determine the parameter of the island. Okay, we just go through and okay, there are many ways to do this, I suppose. Exactly one island. Yeah, so it's 16 yellow stripes in the image proof, so it's 16. Okay, so there are limitations, right? Since there's only one, so we can just go, I think a BFS, not a BFS, a DFS shall work, right? You start from any one, and then you start going. And each time you go out, if it's an adjacent, any side that is adjacent, then that side's edge does not count, right? So if I start from this one, I go up, have 4 directions. Each direction that cannot go counts. The direction that goes doesn't count. Right now you're here, you go up, so this one doesn't count, but this one will count. You go here, this one doesn't count, but these will count. You go down, this one doesn't count. So you go here, and we all do, this and this. Okay, so we also need a visited, which I can do by changing the value into a 0, right? By changing the value into a 0. Oh, be careful. If you change the value into a 0, we're going to go through the thing. You will double count. So I cannot change it to 0. I should change it into a different value. Let's say change it to -1, right? You change it to -1, so you know this side can now go and you cannot count, right? So we'll go 4 directions, right? We have that, and then we check for that value. If it's outside the range, yeah, you count. If it's outside the range, so when you do that, outside the range, we count, and we'll continue, right? If it's a 0, we'll count, and we'll continue. If it's not, right? If it's not, then, so what is not? So if, oh, hold a second. So yeah, they have that, and if it's a -1, we continue, but we don't count. If it's a 1, if it's within, right? If it's within the range, and it's a 1, if it's within the range, we have 2 situations. It's either 1 or -1, right? And if it's a 1, then we can do it. If it's -1, no, we don't do it. But if it's there's a like it's either within or without, right? If it's without, it's outside the range, we just plus. If it's within, then we have 3 scenarios. It's either 1 or 0 or -1, right? And each one will behave differently. Okay. And we can always go with do we search for the first island? Yes, we do search for the first island. Okay. Right, let's do this. We'll search for the first island. Alright, so search for the first island. Let's do this one first. Grid.length. Okay, and then we say int fi equal to 0, right? Int fj equal to 0. Okay, and then we say, wow, fi is smaller than m, while fj is smaller than n, if grid fi and fj is equal to 1, then will break. Ho 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 ho. Then you will break. You only break this. Gosh. Alright, I'm not gonna do it this way. I'm gonna do for fi equal to 0, fi is smaller than m, fi plus plus. Right? Yeah, but you still have this problem. How do I get out? Huh. Okay, so we break. Otherwise, if j plus equal 1, right? So when we get out, we say if if fj is smaller than n, then we break, right? Otherwise fi plus plus and fj return back to 0. Like that, right? You like it? Right, if it's equal to 1, then we'll break. Otherwise, fj, we keep moving on, keep going. When this get out, if it be, So this is finding the first, and then we're gonna do a DFS. Right, we're gonna do a DFS. Private void DFS. Every time we see, we increment the result, or we return. Now I think it's easier to do it this way. Int res equal to 0. Right, void, we just call it DFS. Int I, int j, and grid. Right, int grid. It's fine, we just do it again. Right, so we add ij. So what we're gonna do is we're gonna go look for 4 directions, right? So 4 directions, what we can say is, we can do it here. Int, right, directions, dij, right, equal to new int. So we have 0, 1, right, 0, minus 1, minus 1, 0, and 1, 0. So that's that. So what we can do is for int, right, dd of dij, int di equal to dd0, int dj equal to dd1, right? And then, actually, no, we can just say ninj here. Right, ninj equals this one plus I plus j. Here we go. Now it's going to be computation. If ni large equal to 0 and n j and ni is smaller than m, and nj is larger equal to 0 and nj is smaller than n, in this case, if grid ni nj is equal to 1, right? If it's the next one is equal to 1. And we also need to, every time we visit, yeah, I think it'll be better we do it this way. Okay, didj grid, and let's just pass it int m, int n, so we don't have to do this, right? Okay, when we first get it, we should say grid ij, because I visited it, -1. Okay. Now we do the next one. If it's equal to 1, then we just call dfs ninj grid mn, right? Else, if grid nij is equal to 0, right? If it is equal to 0, then we say rest into plus plus, and that's it, right? That's it. Else rest plus plus, and that's it. Okay, then we done. So we find the first one, and then we just call dfs fi fj, right? That's the first one we found, grid mn, and now we return rest. Okay, let's take a look. Is that correct? Looks to be all right. Let's put some document here. DFS and record an edge only when there is no way to go, no more island, no more land to go. Okay, let's see. Finally, something correct. But it's very slow. I wonder, whoa, if there's anything better than this. We did go through everything once, so I doubt we can do any better than this. How did we do it before? Let's take a look. I counted redundant. Ah, you counter redundant. Yeah, you find the island, and then you go 4 directions. Oh, that is a good solution. I didn't realize that. How the memory usage is so high though? Huh. Yeah, you go through every one of them, and each one you check 4 directions. And every time you go, you have redundant, right? And then you just remove the... Huh. Yeah. You can do that. You can definitely do that. Probably, I think we should try it. Didn't think of that. The first idea I have is this. It's good, you know. Sometimes things happen that you have a good solution before, but you cannot forget how it was arrived. Okay, so this is my solution from before. I think it is better. Okay, I need to copy this. Okay, so we still need to do all this. Grid on length, then n, grid 0. length. We'll kind of put this one here. And we say res equal to 0, right? We have all this. And then we just, go, actually we don't do res. We just say redundant, right? We have redundant and length, right? And for int I, 0I smaller than m, I plus plus, right? For int j, 0j smaller than n, j plus plus, okay? And if grid I, j is equal to 1, then length plus plus, right? And then we need to go 4 directions. So for int dd of di dj ni equal to dd0 plus I, and j equals dd1 plus j, right? And we say redundant. So if ni is larger than 0 and I is smaller than m and j is larger than 0 and j is smaller than n and grid ni and j is equal to 1, that's when we say redundant plus plus. Yeah, so each time we hit redundant. And once we're done, we can say the answer is return 4 times length minus redundant. Not significantly faster, so it is pretty slow. All right, so do we have a better solution than what we just... Yeah, it's all right. Okay, so this one's done. Now we can try to at least think about this problem. Minimum operations to form subsequence with target sum. You're given 0-indexed array nums consisting of non-negative powers, non-negative power of 2 and an integer target. In one operation, you must apply the following changes to the array. Choose any element of the array such that it's larger than 1. Remove nums I from the array. Add 2 occurrences of num I divided by 2 to the end of nums. Return the minimum number of operations you need to perform such that nums contains a subsequence whose elements sum to target. If it is impossible, then return -1. Subsequence, it's not a subarray. Okay, so it says power of 2, so immediately we should turn this into a binary. So 1, 1, 0, and a 1, 0, 0. Right? Yeah. No, that's 4. That's 8. Right, so what we want to go is 1, 1, 1, right? So we need to figure out how, and each time you say you remove it, so basically you just take 1, divide by 2 is just the right shift, right? So we have this, we have 1, we have 10. Now 10 have 1, 0, we just need 1 operation, because we turn this into 1, 0, 0 and a 1, 0, 0, and then we're good. So 1 operation is enough. And of course we can pre-sort everything. I have 1, 0 and a 1. I think that's 8, 16, that's 32, like 0, 1, 2, 3, 4, 5, yeah. And what we want to go is 12. What's 12? 12 is 1, I don't know, 12, 4 plus 8. So 1, 1, 0, no, 1, okay, hold on. 4 is 1, 0, 0. 8 is 1. Yeah, that's 8. Right? It's 8 plus 2. Yeah, that's that. Okay, so how do we get here? So we can analyze this. Right? We analyze this. So the minimum that's required is 1, 0, 0. Do we have 1, 0? We don't have 1. So we need, yeah, we can break this down. Oh, that's actually not right because, yeah, it depends on what we have so far. Oof, how do we solve a problem like this? Because to get to, yeah, so 1 turning to 2. You can say we just do 1, 0, 0, 0 and a 1, 0, 0, right? It could be, you know, 2 can add together to get to that value. So, but, right? But everything is always going to be power of 2. So I think we can break it down, right? So this one can break it down. So it's going to be 1, 0, 0 and a 1, 0, 0, 0. How do we get there? That's a different question, but this is the base, right? We can always break it down into the base, right? So these are the base. And if the base exists already, then we can, you know, just try to use it. And now we don't have the base. Then what? So we say, okay, we can break this down. One operation. Well, if we break this down, one operation is going to be 1, 0, 0, 0, 0. No, I think that's 0, 1, 2, 3, 4, 5. Yeah, this is 16, right? So I break this down, we get to 1, 2, 3, 4. Still too big. So I'm going to break again. That's 8. Right? Now we have an 8. So we say, okay, we got this 8. Now we need this. So break it again. So we need 3 operations. Oh, but in fact, we only need 2. How do we do 2? Oh, shoot. We can add this together. Add this together, become 1, 0, 0. Oh, okay. Wow, and then there will be certain things that's not possible. 36. Or 35. What is 35? One zero 1 0 0 0 1 1, right? 1 0 0 0 1 1. So break it down. We need 0 0 0 0. We need a 1 0 and we need a 1, right? This is the breakdown. We're given 1 and 1 followed by 5 zeros, right? And we have 0 1 2 3 4. So we can break this down into 1 2. No, hold a second. That's already my bad. 1 2 3 4 5. 1 2 3 4 5. Yeah, so we have this, and then we only have, if you add them together, it doesn't fit, right? Huh. Yeah, I think as long as the sum is bigger than the target, we can always find a way. Because the worst case scenario, we can always bring everything back down to 1, and then you can just add them together, right? So yeah, the only impossible case is this. That's actually very trivial, right? It's very trivial. Okay, okie dokie, okie dokie. How are we thinking? Well, we have to take a look at the Jesus. Mm. It's gonna be something. And the thing is, this is not necessarily like, you can break this down to other, but no, breaking down to others. It doesn't really matter, right? Does it really matter? All we want to do is break down the numbers, right? Break down this so that I can fit into this target. Hmm. Okay, if you bring a thing down, like 32, you can bring it down to 16 and 16. And their sum is always going to be 32, right? So if you have some value that's bigger than the target, and if you want to use it, you have to bring it down. And when you bring it down, you almost always only use half of it. Right? There's no point of using both. And you have to bring it down to lower. So okay, we can say okay, so we can group the ones. Yeah, like the ones that's smaller. Yeah, we can sort it like this, right? And you just start adding the ones that's smaller than the target. Uh-huh. So you get a sum. Then you have the first one that's bigger than the target. And this one cannot be used by itself, so you have to break it down if you want to use it. Right? You have to break it down if you want to use it. And you have another one, you can also break it down. Right? Like if you want to use it, it has to be smaller than the target. Because if you break it down, it's still bigger. There's no way. Right? There's no way. So I have a bunch of value that's smaller than the target. Okay. And the question is, can we, right? Yeah, so we have a bunch of values. So we have a bunch of values that's smaller than target. Okay, we have an array of values. They are smaller than target, right? And we need to figure out if we can get to target. Some sort of sum, right? We'll get a target. How do we figure that out? Okay, so if the target ends with a 1, right, something, then we know we must have a 1. If we don't have a 1, then something need to give me a 1, right? If the target ends with a 1, 0, then we either have a 1, 0 already, or we need to break into 1, 0. Or if we have 2 1s, right? Because all we want to do is try to fit the final value, right? And the final value we find the least significant one will be a 1 followed by some zeros. So that is the most, like, the least significant one that we need to form. And to form that, there's only one way to form that, right? I don't think so. Right? Like, we can do this and this. That's a 2. That's a 6. Right? This one going to this. So there are different ways to form. But we can say, okay, a 6 isn't 6 is also just going to be a this and this. Right? And that will be like this together, and then, yeah, so everything can be, built up towards what you want. Right? So let's say if we want this, like, how do we get it? We can say if we want this, then we need to get this. We need to get this, right? To get this, we need this. And if we have one, then we're good. If we don't have one, so we need to get this, then we need to get this and this. So we need to see if we can have this. What do you think? So I have a target value. Okay. I find the least significant bit. Then we try to see in the current available, do we have it? Do we have it? If we have it already, we just use it. It's like a greedy, right? If we have it, we just use it. If we don't have it, then we'll break it down. Divided by 2. Right? We say, what's the minimum that I'll take? Minimum operations to get each component. Minimal operation to get each component. But as you do this, you're making changes as well. Okay, so yeah, so we get a 100, and then you say, okay, do we have a 100 in our pool? Right? If we don't, if we don't? What are you gonna do if we don't have one? Right? We want a 4, but we don't have a 4 in the pool. Then you go what? What do you do? So you can try to add. Can we do it, like change what you're trying to do, right? So basically, in this case, right, let's say we give them 1 and 2. Can we make 7? We can't, because the sum is smaller, right? So we need to add something bigger, right? So now, but we know 8 is too big, so we say, okay, for 8, let me divide. So now we have 1, 2, 4, and 4. Can we make 7? And then we say, we can do 1 plus 2 plus 4, and that becomes 7, right? That's kind of one way to think about this. So in this case, we start with 1, 1, 2. Can we make 12? No, we cannot. So we need help. So now the next bigger one is 32. So we say we'll get, it has to split, right? And it has to split. But even after split is not going to do, so we have to split again, right? So it's become this. And then we put a in there, right? So we have 1, 1, 2, 8. We can say actually 2, 8, 8. Right? And then we have 16 left on the outside. We say, can this make 12? And the answer is yes. But okay, how do we check if an array can make into a value? How do we check that? And it's subsequence, right? It's subsequence. I don't know. What's the size of num? 1000. Yeah, I don't know. I don't think that's right. If you like, it's like each one, it's like just with 2 to the n, because each one you have 2 options, right? Either take it or not take it, and then go down. And this one have basically from this to the end, can we make 11 or can we make 12? That's the value, and then times, I don't know, because the value is just like 2 to the 31st. And even if everything add together is bigger, they might still need to split, right? Or might still need to split. And it might be that if we split the bigger ones, it'll give us a better. Oh, this is tough. This is very tough. I have no clue. How? What's the angle into this? Yeah, what's the angle into this? All right, I'm gonna look at a hint. Absolutely no idea. Okay, greedy and bit manipulation. So greedy. What do you think? Greedy. Well, if we really do greedy, we can say that everything that's smaller, we always try to fit all of them. That's not true, right? That's not true. Because what if I do, I don't know, so for 12, you have to split. Because I'm thinking, what if I just split a big one and then into the target? So we only do it once. But if we try to add, then we have to do multiple times. Right, in this case, what if I say target is 16? Okay, if target is 16 and I say I'm going to just remove all of these, that's a 4. Right now we have a 12. Basically, we say we have 32, then we need to get a 12. Then you have the split. You have the split again. You have the split again. Yeah, you have to do like 1 split, 2, so 3 splits. Right, so it's different. The greedy must happen differently. Okay, it's not getting all of them, right? It's done differently. Okay, so there's another way to do greedy, because we know 12 is this, right? So another way to do greedy is we will get 100 first. But then we have an issue. We don't have 100. Then you can say, okay, I'm gonna break 32 into 100. But that's not true, because the right way is to combine 112 into 100. See that? How even do greedy? All right, I don't know. All right, hint number 1. That's correct. We got that. Hint number 2. Solve the problem for each set bit of target independently from least significant to most significant. Okay, that's okay in our mind as well. Okay, what's hint number 3? For each set bit of target from least to most significant, let x equal to some nums I. For nums I is smaller or equal to 2 to the power of bit. So they're sum up everything that's smaller than that. So that's the greedy part. But why? We sum them up. That's fine, right? We have whatever the current we're looking at, and then we add them all. And and what do we say? If it's bigger than, then we use that to fit. If it's smaller than, what if it's smaller than? Okay, keep going. If it's larger than, repeatedly select the maximum nums I. Such a nums I is smaller than this. That has not been selected yet until the sum of selected elements equals. The selected nums I will be part of the subsequence whose elements sum the target. So those elements cannot be selected again. I do not understand a bit what this is trying to talk about. If x is larger, so if we are larger than the target, no, not even the target, we're larger than 2 to the bit, repeatedly select the maximum nums I. So what do you mean by repeatedly select? Such that nums I smaller or equal to 2 to the bit that has not been selected yet. Until the sum of selected elements equals 2 to the bit. repeatedly select the maximum nums I such that nums I smaller or equal to 2 to the bit that has not been selected yet. Until the sum of selected elements equal to that. The select num I will be part of the subsequence whose elements sum to target. What? Okay, let me think about it again. So what it's trying to say is, if we find so we have a 2 to the power, right? And then we have a bunch of others, and these are all smaller than the current 2 to the power, right? And if their sum is bigger, then they're always going to be a way such that their sum is going to be equal to y. Because they're all power of 2. Okay, they're all power of 2. And we have some way such that their sum is bigger than. Is there a theorem of this? If you have a bunch of power of 2 and their sum is larger than the current, larger than a target power of 2, right? Then we say it's guaranteed that a subset of those power of 2s can add up to what we want. Because it's larger than the power of 2, right? Because when power of 2, when you add, right, and then the target is a power of 2, so, and the sum of all the power of 2s, if it's bigger than that, it's bigger than that. So we have this plus this, now whatever you plus, right? Because it's bigger than a power of 2, then the ideal is you must go through that power of 2 in order to get bigger than that, right? You must go through it. You cannot skip it. Well, the reason you cannot skip it is to get beyond this. To get beyond this. And if they're all smaller, then you have to go through this, right? You cannot skip this in order to get a bigger value, because when you move the set bit to the left, right, you have to. There's just no way. You have to go do that. Okay, so basically this is saying if all the numbers that's smaller than the current 2 to the bit, right, and then their sum is bigger, then we always going to find a way to sum them up into the smallest one. And we will try to use the biggest possible, right? Okay, I see. Okay, I think this is okay. I agree. And then that's when it's larger. And when we use those, then those gets removed. You cannot use it again, right? Then you move on to the next biggest, right? Next largest bit, next least important bit, and you try it again, right? You try it again. You try add them together, right? You try add them together, and you will say, right? You will say that If it's bigger, then you can still do, so you don't have to. But if it's smaller, and what happens when it's smaller? Then we need a bigger one to split. But here is what I am confused. Who splits? And for how much? This is the last hint. Add 2 occurrence without moving to the next bit. Go back to step 3. So we just do it all over again. So we pick the smallest that's bigger, one of them, we split. Then we add 2 new to, okay, so that is the exact same, I shouldn't say exact same, but we have this idea of, just given this, can it reach? But yeah, we don't reach 12. We shall reach the power of 2. What can we reach? Because that there we can say, if we can reach, we remove those. And then we go to the next one. Can it reach? If we cannot, we find one of the bigger ones, split them, right? Split them and put them in, right? And then we see if it's smaller, then we put them in here. If it's bigger, then we record one and then we take another one and we split it again, right? We push it in. Holy crap. Wow, it's pretty tough. I think the most significant piece of logic is to realize that given a power of 2 and a list of power of 2 that's smaller than it, if their sum is bigger than the power of 2, then there is always a way for them to equal the power of 2. I think that is exactly the same thing. It's just a binary, right? When we do a decimal, right? When we do a decimal, if I have a bunch of numbers that's smaller than some value and their sum is large, that's actually not true. I can give you a perfect counterexample, right? You can have, I have 5 and I have 2, 2, 2, right? 2, 2, 2, everything is smaller than 5. Their sum is larger, but we don't have one to get to 5. But if we have a binary value and everything is smaller, no matter what is smaller, and their sum, if their sum is bigger, then there got to be a way for them to reach here. Now the reason is, I need to find a good way to explain to myself or convince myself that this reason works. Because as we add these to get bigger than that, right? So the bit need to move left step by step, right? Need to move left step by step. And no matter what happens, to be bigger than this, we have to move to this state for once. We have to move to this state for once. No matter what happens, we have to move this, right? And because we can reach here, so we can definitely find a subset of these values to sum up to this. Okay, I think that makes sense. But the second one is when we do greedy, we say we always want the big values first. That's what this one says, right? We have to find the maximum. But why do we always find a maximum? Like, what's the benefit of always using a maximum? Well, the benefit is if we use up the smaller ones, then they are not replenishable. But to replenish them, we have to split more. But if we use the bigger ones, then they're more easily replenished, right? Because if we use the smaller ones, then we not only have to split the really big values, but also split these medium values. But if we use the median values, we only need to split once. That also makes sense. Okay. Okay, so we can do this, but yeah, it's tough. Very tough. All right, so that will be it today. I'm not gonna implement it today. I'll do it some other time.